Hello students, Mr. Dana Howard here. Welcome to another lesson in ESS. And again, I'm sorry I'm not with you today. This is a fun lesson when I'm there, but we're going to make the best of it we can. So we're going to be talking about density today. And to start us off, I have two balloons here, a red balloon and a yellow balloon. The red balloon, I just filled up by blowing air from the atmosphere into it. So if you don't know, most of the air in the atmosphere is nitrogen, and the second most abundant type of air in the atmosphere is oxygen gas. And then there's trace amounts of other gases as well. So mostly what I've put into this balloon is nitrogen and some oxygen when I exhaled, because you do exhale oxygen, or else if you didn't, if you only exhaled carbon dioxide, then mouth-to-mouth resuscitation wouldn't work, right? So we do exhale some oxygen and a little bit of carbon dioxide, but not very much. So when I let this balloon go, it sinks, right? This balloon is filled with helium. And as you know, if you have a balloon filled with helium gas, it's going to rise. Okay, hopefully it doesn't fall and hit me on the head while I'm doing this lesson. So we're going to dig in a little bit to density. Why does the yellow balloon with helium float and the red balloon with the other gases sink? And it all has to do with density and differences in density. So we're going to dig into that today. Density has, it's another fundamental concept, just like our phases of matter. And we're going to tie phases of matter and density together in this lesson. But it's another fundamental property of matter. So we're going to dig into this lesson. And if you would grab your note sheet that you should have by now, and it is a fill in the blank. I'm not a huge fan of those, but it'll get us going here and help you focus on the lesson and not as much on trying to take some notes down. So what is density? Density is a measurement of mass per unit of volume of a substance. What that means is if I have a certain amount or mass of a substance and I know the volume, then I will know the density. And anytime you're working with any material that is made up of just one substance, typically, for example, water or oxygen gas, the density at a specific temperature is going to be the same for all of that matter. So if I have a cup of water and it's at room temperature, which is about 20 degrees Celsius, right? Room temperature, it's all water that's pure water at room temperature is going to have the same density, which you should know is about 1 gram per milliliter. That's an easy one to remember. So you can see on my graphic here, right? Here I have an object, and there's kind of an imaginary box around these two objects here, and they're contained. And you can see the size or volume of the actual box that they're in is about the same volume, okay? But here I have, by the way, what phase of matter would this be? Let's pause for a second. What phase of matter do you think this is and why? If you answered gas, you're correct. And how would we know? Because the particles are not touching, right? They are spread out from each other. On this side of the teeter-totter, I guess, we have a lot more matter. Okay, so there's going to be higher mass in the same amount of volume. So this would be an example of something that's high density. What phase of matter do you think this is in? And if you said solid, to me, the particles are definitely touching, which means it's got to either be a solid or a liquid, because the particles are touching in both those phases of matter. But it kind of looks like there's a crystal structure here, like a pattern, the way that the solid atoms are put together. And so I would vote for solid on this, but it could be a liquid that's just really full to the top of the box. So anyway, point is, if I have less matter or stuff in the same amount of area, it's going to be lower density, and more matter in the given area is going to be higher density. Okay. Now, I want to make a clarification. Sometimes people use mass and weight interchangeably, meaning they use them to mean the same thing, and they are not the same thing. So mass is a measurement of how much matter something contains, right? The only way we can change that is if we take some of that matter away or we add some matter. So if I had a chunk of gold, right, the only way I can change the mass of it is I cut a piece off, or I take the or I somehow I add some gold to it. So if I heat it up and melt it to maybe make a a pendant or something like that, or a necklace, some jewelry. If I do that, if I face change, the mass does not change. Okay. Now, weight is different. Weight is dependent on gravitational pull. So the gravitational pull on Earth is pretty consistent. It is usually about 9.8 meters per second squared. And that's consistent, pretty consistent no matter where you go on Earth. It changes very slightly, but not enough that we would actually be able to tell without very sophisticated equipment. But if we took my gold bar, right, to the moon and got the weight of my gold bar, the weight would be different on the moon because the moon has a lower gravitational pull. It's about, if I remember, about 1/7 of the gravitation that we have on Earth. And that's why when you see the astronaut jumping here, he can jump a little higher and it almost seems like he floats a little bit because he's on the moon and there's less gravity on the moon. So mass is not dependent on gravity. Another example would be the space shuttle. In if I took it and put it in the middle of space where there's no gravity, okay, not in its orbit because there's gravity in its orbit, or else it would just fly off away from the Earth. But if I put it somewhere in the middle of space and there was no gravity around, the mass would be the same. The mass would be the same, but the weight would be different than the weight of the gold bar on Earth. So that's an important concept. Now, when you're out just talking to people and you use mass and weight interchangeably in out in the world, they probably know what you mean, but in science they mean very different things. And so 99% of the time whenever we talk about or we take measurements and scientific investigations and things like that, we are going to use mass. We are not going to use weight. And the balances that we'll be using, which you'll be using in the lab tomorrow, we will want to use mass for those because when we're calculating density, it's mass over volume, as we'll see soon. All right, let's keep cruising here. Another thing that I want to mention, this is kind of like the first slide, so just another visualization. This object is going to be less dense, assuming we're assuming two things. Number one, both of these green particles, whatever they are the same thing, okay? And the size of the box, the volume is the same for each of these. More particles, more mass or matter in this box, so it's more dense. Less matter in this box, so it's less dense, okay? So two things I want to point out. Number one, why does density matter? Like, what are we doing this for? Density, as I said, is a fundamental property of all matter. So if let's say I develop some new material, and there's a whole field in engineering and chemistry called material science, and material scientists, their whole goal is to develop new materials that we might be able to use that are lighter and stronger, have less of a carbon impact, like carbon footprint, or less chemical usage, lots of things like that. So when they do that, let's say a scientist makes this great new material and they're going to use it in space because it's really strong and really lightweight. Well, we need to know the density of that material so that when we do calculations on the satellite it's going into, we know the mass that it's going to have. And this is important because density doesn't change no matter what the object is. It can change because of temperature changes. But if we have the same substance, density is what we call an intrinsic property or an intensive property. No matter how much I have of that material, the density will stay the same. Back to my gold bar, right? If I have a tiny piece of gold and next to that tiny little piece of gold, I have a big bar of gold, which if I had those, I don't know if I would still be here teaching you. Well, yes, I would. I enjoy this. But I would enjoy having big bars of gold. I lost my train of thought. Okay, if I had those two, right, the density of the gold in each of those objects is going to be the same because it's gold, and we're going to assume they're at the same temperature. Okay, so that's a key concept with density. Mass changes depending on how much stuff you have, so it's less useful for certain things. There's other properties too that are like density in this. Okay, let's keep going. So here's a few common objects that you guys have, that have lower and higher densities. So in general, this is just in general, helium gas. I would reach my yellow balloon, but it's on the ceiling and I can't reach it right now. Air in general, any gases are going to typically be a lower density, right? Many of our plastics that we develop through chemical processes, those are usually lower density compared to some of my other things over here. Pine wood, gasoline, alcohol, these are all lower density materials. Okay. And keep in mind, like gasoline is a mixture of a whole bunch of different things. It's got a bunch of different hydrocarbons in it. But when we just take gasoline in general as a substance, we can get its density and use that to determine some of the properties and compare it to other substances. So, what things have higher densities, as you probably know, metals, harder woods like oak, beech wood. Those are all like harder materials, so they have more matter per area than these do, and so they're going to be a higher density. All right, now we're going to get into some calculations, but actually, before we do, let's go back to the balloons. Well, no, we can't do that. We'll come back to the balloons in a second. Okay, so I'm getting excited to talk about the balloon. Let's talk about calculating density really quick. Okay, how do we calculate density? It's a simple mathematical calculation. Density is equal to mass divided by volume. Now, you might be wondering, what is this p, lowercase p thing? This is the Greek letter rho. And rho is the symbol that at some point scientists decided to use to denote or show density. So whenever you see that lowercase p, it's probably referring to density. If you write a D for density, D equals mass over volume, that's fine. But I will be using the Greek letter rho because that's what we've adopted in science. Okay. Now there's some different units we can use. So let's say you look up the density of helium on Google. You just Google it right now and you look it up. You could get a whole bunch of different units. Why? Because there's a bunch of different units for mass, right? Grams or kilograms, and there's others as well. In the volumes, the same way, there's a lot of different units. And so you kind of have to pay attention to the units you're working with and make sure they're matching up when you're doing calculations. Normally, whenever we work with mass, we're going to be using grams. Okay, but you may see things in kilograms, but we're going to be using grams. And in volume, we're going to be typically using cubic centimeters or centimeters cubed or milliliters. Okay, those are the two that we're going to be using. And just so you know, 1 cubic centimeter, so a centimeter by a centimeter by a centimeter, that's the same amount as 1 milliliter. You might have heard this stated differently. If you ever watch medical shows or anything, they'll often use the term cc's, right? So the doctor rushes in and says, give him 20 cc's of epinephrine stat. And that's cc is referring to cubic centimeters. So 20 cc's is the same as 20 cubic centimeters, which is the same as 20 milliliters. Okay. So just a little bit of background information for you on these. You may see meters cubed and liters used for volume as well, but in our class, we're going to be using the ones I just referred to. So we are going to be doing some calculations. If you have your calculator, which I hope you do by now, because you're going to definitely be using it a lot over the next few days here, please take that out. And let's do a couple of calculations. Now, before we get into the practice ones, I want to let you know, make sure you jot down some work on these and maybe even a few notes so that you, tomorrow when we're doing the lab, you are comfortable with doing these calculations. Tomorrow, I'm going to give you 3 different substances on your team, and you're going to have to make a prediction on what you think that substance is based on your density calculations. So you need to be able to do some measuring and calculating for the lab tomorrow. Okay, first one, what if you have, actually, let me start with mass. Mass is pretty easy, right? We take our substance to the balance, which you'll see in the room tomorrow if they're not already there or here. You'll see the balances. We're going to make sure they're in grams. We're going to put our substance on the balance and get the mass. Now, if you have a container, let's say you are using a liquid and you have a container that the substance is, and you're going to have to subtract away the mass of the container. And you can use the tare button or 0 button on your balance as well. Put the container on, zero it out, and then add your liquid to it to get the mass of it. So we'll be doing that tomorrow. Let's go back to this. So for a rectangular object, if you can measure the sides and they're, relatively easy to measure and it's not some funky shape like this rock here, then we can just measure length, width, and height and multiply those together to get the volume, right? Volume equals length times width times height. Now, how does that give us centimeters cubed? Length is in centimeters. That's because that's the standard unit we use in science. We don't use like inches and feet. So we're going to use centimeters in this case. We would measure the length. We would measure the width in centimeters and the height in centimeters. When we multiply all those together and just focus on the units, we have centimeters times centimeters times centimeters. And that makes centimeters cubed. Okay, that's how we get that number. So for this one, let's go ahead and bring up the whiteboard. For our first problem, we don't really have to do many calculations. It's already given us the volume and the mass, but make sure that you are paying attention to which one is which. So in the problem, it tells us that the volume, I'm going to do my best to write this legibly on my computer screen here. My volume is 2,072 centimeters cubed, and I'm always going to put my units with my numbers so that I don't forget what it is that I'm actually using for my numbers here. Okay. All right. Now it tells us the mass is equal to 5180, 5,180, and that is in grams. So I know it's my mass. Okay. Now, anytime I work a problem like this, I'm always going to write down the things that I know. Okay. These two. And then what I'm looking for, I'm looking for density, which remember we're going to use rho. So I've written down, I know mass, I know volume, I'm looking for density. And now I can write this formula down. I know that density equals mass. Come on, write for me over volume. And I'm just going to go ahead and continue that equation here. Pay attention, right? This one's mass. So mass goes on top, mass over volume. And I'm going to do 5180 grams on top. I'm going to keep my units in there. It's always important to write your units down. A lot of students are not in the habit of that, but please get in the habit. As you get to more difficult math that's in science and math classes, it's going to be very helpful to have your units on your numbers. Volume goes on the bottom here, and this is my volume, 2072, and that's cubic centimeters. So when I divide these two, right, 5180 divided by 2072, my number is going to be 2.5. I have a lot of students ask, well, how should I round this? So if I get some long string of decimals here, what do you want me to round to, Mr. Danahauer? And honestly, I don't really care. We're not launching rockets here, so we don't need a bunch of decimal places, like very accurate numbers. I just want to see a little bit into the decimal there so that I know that you got the right answer. Okay, so feel free to round to 1 or 2 decimal places. That's fine. Now we need our units. And so all you have to do is follow your units here, right? We have, come on, right, grams divided by cubic centimeter. And so I'm going to write grams per cubic centimeter. Okay, so that would be our answer for the first problem. You'll be doing this again a lot tomorrow. Okay, let's go to the next one. And sorry you don't have the slide up here, so let me put that back up for you in all of my stuff. Sorry if I can find it. Okay, so here we have this one, a green rock. So it has a mass of 151 grams. Now this, we can't measure the size. Imagine trying to measure every little side of this and calculate the volume of it by measuring. That's not efficient. There would be no good way to get a good number here. So there's another technique we can use, and that's called water displacement. So what we're going to do is we're going to get a graduated cylinder and we're going to fill it with enough water that we can submerge this rock into. And we're going to make sure the graduated cylinder, like the rock, will fit in the graduated cylinder and not get stuck. That's another important one when you're doing this in the lab tomorrow. So I'm going to put some water I'm going to jot down the number before I put the rock in. Okay. And then I'm going to add the rock and see what the new volume is. What will happen is, of course, whenever we put the rock in there, it's going to displace or push out some of the water, not out of the cylinder, but it's going to raise the volume of the water because we have the rock in there now. So that's called water displacement. When that rock pushes the water out, it's going to push out, it's going to raise the water level, the amount or displace the amount of the volume of that rock. So all we need to do to figure out the volume is subtract these two numbers. So let's go to our whiteboard and we will do that calculation here. Oops, let me get back to this. Sorry. Okay, so let's write this out together. Our rock, the mass is easy, right? We just stick that on the scale and it's 151 grams. And then our volume, so the way we're going to figure this out is we're going to do V final, our final volume after we added the rock, minus V initial. Right? Your initial volume is always going to be less than the final volume, so it makes sense that we want to subtract the bigger number goes first minus the smaller number, or else we get a negative volume, and that doesn't really make sense, right? So let's carry on that calculation right here. The final volume was 76 milliliters, and I'm going to subtract the initial volume, which was 20 milliliters, from this. Okay, so my volume for this is going to be 56 milliliters. So I know the volume of the rock is 56 because that's how much the volume increased when I put it into the graduated cylinder. I should have put up a picture of a graduated cylinder for you. If you don't know what that is, we're going to be using them tomorrow. Usually they're glass or plastic. They're shaped like a cylinder, right? And they look kind of like this, and they have graduations, which is a fancy way of saying the tick marks for doing the measuring. So this is a graduated cylinder, and it's called a graduated because these marks are called graduations. That's not a fancy name for saying it's really smart because it's graduated college or something like that. Okay, let's back to our calculation. Our goal is to find the density. Oops, turn the pin on, Dana Hauer. Okay, our density is what we're looking for, right? So I'm going to come over here and write down my formula. Density equals mass over volume, and let's plug that in. You guys are probably doing this faster than I am. You should be doing this with me to get to practice. If you're not, engage. All right, so you have our mass on top, making sure that I've got mass on top, and then the volume on bottom is 56 milliliters. Okay, so notice in the last problem, our mass was in grams and our volume was in cubic centimeters here. But in this problem, our volume is in milliliters. So like I said, either one could be used whenever we're working with density. When we plug that into the calculator and do 151 divided by 56, quick gut check, right? If this was 50, if it was 150 divided by 50, it would be about 3. And so that's a good way, when you're doing calculations like this, just if you can do a quick estimation, like, we should get a number right around 3-ish, something like that. So, and our number is actually rounded, is 2.7. I think we get like 2.769 or I don't know, something like that, but it's 2.7, and make sure to include your units, grams per milliliter. Okay. Good. So that's a couple of examples of calculations we might be using when we're working with density and trying to determine the density of objects. Let's come back to our slideshow here. Okay. So why does that matter? Now we can talk about the balloons thing. Okay. This red balloon, I don't have the yellow balloon because, like I said, it's up above me. But things that are, let me back up. The density of water, as I mentioned, is 1 gram per milliliter, and that's a number you should remember. Okay, when water is at, I believe, 20 degrees Celsius, which is room temperature, it's going to be 1 gram per milliliter. If you change the temperature of the water, the density may change just a little bit. Unless you phase change it, and then it's going to change a lot. But if it's just changing the temperature of the actual liquid water, it may be slightly higher or lower than 1, but not much. Okay. So objects, when we put objects in water, If they are less dense, they're going to float. So think about bubbles in your soda when you open it. Bubbles, if they form on the bottom, they're a gas. The particles are spread out really far, so they're very low density, and they're going to float or rise up to the surface, right? If objects are more dense than water, they're going to sink. So if I took an iron nail and dropped it in water, iron is much more dense than water. I think it has a density of around 9 grams per milliliter per cubic centimeter. That's going to sink. So objects that are more dense are going to sink in water. If they have the same density, so let's say I have a material and it's the exact same density as the water, it's going to suspend, meaning wherever I push that object to in the fluid, in the water, it's going to stay in that spot. That's called suspending. All right. Not many objects are going to have the same exact density of water, but there have been some creative drinks out on the market, fun, tasty drinks. Like I remember when I was growing up, they had this one called Orbits, and inside of the drink, they had these little balls that were, I don't know what they were made out of, but when they developed that, they made them the same density as the drink. So they would all just suspend wherever they were in that drink, and you would actually drink them with it. And it wasn't very good, so I don't think it exists anymore. But it's a good example of suspending. Okay. All right. I keep saying back to my balloon. So what if it's not water? What if you're putting something in an object into another substance? The same thing is true. If the density of the medium, okay, so like the medium that I'm in right now is air, right? I'm surrounded by air pretty much. And the density of air is pretty low. Uh, but my balloon, I filled with air, but it also is made of this rubber, right? So it's kind of made up of two different things. So when I put this balloon in the air, it sinks because it's more dense than the air around it. All right. It's going to fall. If I grab my helium balloon, okay, picture, I've got my yellow helium balloon now, okay. If I grab that and let it go right here, it's going to float. And that's because helium, atoms of helium and molecules of helium, they weigh much less. They have less mass. Oh, see there, I did it. I used weight, right? They have less mass than regular air that we breathe in and are surrounded by. So even though even though I put air into that balloon and it's pretty much the same as the air around me, the rubber actually makes the whole balloon more dense, so it sinks. The helium balloon is less dense because there's less mass. I tried to fill those balloons up about the same amount too, so they should be pretty similar in volume to each other. So that's a good application. It doesn't matter if we're putting something in water or air or some other liquid or gas. We can always make that comparison. If something is floating in that medium, it's less dense than that medium. If it's sinking, it's more dense than that medium. Okay. All right. We're going to skip our candy bar one. We did some good calculations there. And so I've got a couple application questions. And actually, before I do that, I want to give you one other example. We talked about, let me pull up my whiteboard here again. We talked about what if you have a regular shaped solid, right? We can measure the sides and do length times width times height for a solid. If we have a solid that is in a regular shape, a weird shape, we can use water displacement. So we can use length times width times height for one. That's one option. Number two is water displacement. Sorry, I'm writing quickly here and I don't like writing on this, so I'm going to abbreviate. The third is what if you have a liquid, okay? What if you have a liquid and you need to determine the density of a liquid? We can't use displacement because I can't take water and put it in my graduated cylinder and then add a liquid to it. That wouldn't work very well. So how could I do this? So here's a procedure. I want you to jot this down because you're going to use it tomorrow in the lab. I'm going to give you a liquid. It's going to be an unknown liquid and you're going to have to determine the density. When we determine the density of a liquid, One strategy is to get our graduated cylinder, and you guys are going to figure out that I'm terrible at drawing stuff, and so bear with me. All right, and we've got some numbers. This is our balance. Okay, so balance. So you're going to take your graduated cylinder and you're going to put it on your balance. Okay, then you're going to zero it out so that it's not going to account for the mass of the actual graduated cylinder. So when you do that, you put it on here, you hit zero, the scale will take a second and it will zero it out and it will read zero. Then you're going to add your liquid. Okay, so that's step 3. Step 1, put your thing on the balance. Step 2, zero it. 3, add your liquid, and you don't need a lot. I would say, add about maybe 10, 10 milliliters of liquid. All right. And then get the new mass. So you'll take the mass, and it will only be giving you the mass of the liquid because you zeroed it out in this step here. Okay. Uh, then you can look at your graduated cylinder and get the volume. So you're gonna read after you take the mass. You can take it off the scale and read the graduated cylinder to get the volume. Okay. Then you'll have your mass and the volume, and you can calculate the density. All right, let's go back to the slideshow. We're about finished up here, and take a look at a few application questions here. So these are just kind of, why does density matter? Some things to think about. All right, so one is an oil spill. You might remember some famous ones like the Exxon Valdez that spilled a long time ago, actually, up in Alaska. And they, according to Department of Energy, these numbers could be a little old. So 1.3 million gallons of petroleum, that's another word for oil, are spilled into U.S. waters every year. Now, you might know oil typically floats on the surface of the water. So, what does that tell us about the density of the oil? Well, we can't get the actual density. We could look that up, but it tells us that the density of oil is less than the density of water. So, it's going to be rising to the surface. An interesting fact about that is as the oil is exposed to sun and other chemicals in the ocean, it actually changes chemically and becomes more dense. So after about a week or so, all of that oil starts to sink to the bottom of the ocean and mess with our biosphere in that way. So another one. Oh, I already kind of talked about this. So we talked about what's the density of air compared to that of helium. The density of helium is very low, and so when we put a helium balloon in the air, it's going to rise since it's less dense. Okay. Here's one that we'll talk about not too long from now when we get into our geosphere unit and talk about the composition of the different layers of Earth. So scientists theorize, geologists theorize that when the Earth first formed, it was a hot mix of melted elements and compounds. Okay. Now, these elements and compounds have different densities. And since it's easier for liquids to move around than it is for like solids, it was important that as the earth cooled, the layers started to form due to density differences. So layer chemicals and compounds that were more dense sunk to the center, like iron and nickel. And our middle layer is made up of less dense, and then the least dense layer is the top layer, which we consider to be the crust. Okay. So those are a few application questions. And unfortunately, I'm not going to have a chance to do demos. So hopefully I'll save demos for you for next time. That's it for today. Check out the formative that I have for you that will be assigned and due tomorrow before we do the lab. And have a great day. Sco Ridge.